Okay. So thank you all for those who are watching this, both at the time when this is being recorded and later on. So this talk is about lifting maps between graph system algebras to maps between the underlying Leavitt path algebras. Let me start by the first slide to fix notations and conventions. Well, E will be a graph, a directed graph, consisting of a set E1 of edges, a set E0 of vertices, and two maps, the range map R and the source map S. I will assume today that my graph is finite. All my graphs will be finite, meaning that both E1 and E0 are finite sets. So it has finitely many edges and finitely many vertices. I will also assume that my graphs are regular, which for a finite graph means that they have no sinks, where a sink is a vertex that does not emit any edge. In other words, assuming that a finite directed graph is regular, or that it has no sinks, is assuming that S is onto. Okay? So under these assumptions, the incidence matrix of E is a square, finite square matrix indexed by the vertices of E, whose entry at the VW spot is the number of edges that go out of V and land in W. I will also be considering what I will call the Bowen-Franks group, which is the co-kernel of the identity minus the transpose of the incidence matrix, regarded as a map from the abelian group, free abelian group on the vertices of E to itself. So the canonical, the member of the canonical basis of this free abelian group corresponding to the vertex V, I call it simply V. And then I consider a distinguished element in the Bowen-Franks group, which I call 1 sub E, given by the sum of the classes of each of these generators, each of the vertices. I will write LE for the Leavitt path algebra of E over C over the complex numbers. This is generated by, it has one generator for each vertex and two generators for each edge. One, the edge itself, and the other one, the involution applied to the vertex. So this is an algebra with an involution. It's a star algebra, so the involution fixes the vertices, maps an edge to its ghost edge, the E star, and on the coefficients, on the complex numbers, it is given by complex conjugation. So it is a star algebra in the operator algebra sense, which means that you can consider star algebra representations, star homomorphisms, into bounded operators in Hilbert space. Each of them gives you a semi-norm, and take the supremum of all of them, that's a norm. You take the completion of the Leavitt path algebra, and you get the C-star algebra. The C-star algebra of E, the graph C-star algebra, or Cuntz-Krieger algebra, named after those who first considered it. Okay, and I will also use a term, SPI, which stands for simple purely infinite, And I will apply this term, this adjective, to, let me see, to the graph. So I will say that the graph is simple, purely infinite, or SPI, if it satisfies the conditions of the hypothesis of the purely infinite simplicity theorem, which are equivalent to requiring that LE be simply purely infinite, and also to requiring that the C-star algebra be simply purely infinite. Okay. So now we move to the Kirchberg-Phillips problem. So this starts by a theorem, which is not a problem, but a theorem, which says that if E and F are SPI graphs, finite SPI graphs, which have the same Bauer-Frank invariant, so that is, there is a group isomorphism between the Bauer-Frank's group of E and the Bauer-Frank's group of F that carries the distinguished element to the distinguished element, then the C-star algebras are isomorphic. This was proved by Kuntz and Rordan. I mean, it was proved by Rordan using some ideas from Kuntz, and later on was subsumed by a more general theorem on Kirchberg algebras proved by Kirchberg and Phillips. So the numbers refer to a list of references that I will show you at the end. And this raises the obvious question that was put in paper, in print by Elbrand, Sand, Lowley, and Pardo, on whether an isomorphism, such an isomorphism, that is the same hypothesis of the Kuntz-Rordan Kirchberg-Phillips theorem, whether they also imply that the Leavitt path algebras of E and F are isomorphic. Now, LE and LF are algebras, and as I said before, they are also star algebras. So you may ask whether an isomorphism of the Bauer-Frank's invariants implies an algebraic homomorphism, or you may even ask whether there is a star algebra homomorphism. So whether they are isomorphic in the category of algebras and algebra homomorphisms, or in the subcategory of star algebras and involution preserving homomorphisms. An important difference is that if you have a star isomorphism of Leavitt path algebras, then it automatically passes to the completion and induces an isomorphism of the corresponding C-star algebras. So if the answer to the isomorphism question in the category of star algebras had a positive answer, this would say that whenever two SPI graph C-star algebras are isomorphic, they are independently of whether the isomorphism you found was algebraic or not. There is another one that is algebraic. Okay, algebraic in the sense that it comes from an isomorphism already defined at the Leavitt path algebra level. And so what we showed with Diego Montero in a paper that appeared in Advances, I think in 2020, that under the same hypothesis of the Kuntz-Rordan theorem, the Leavitt path algebras, LE and LF, are not isomorphic as algebras, but isomorphic in the homotopy category. So what do I mean by that? Well, there are algebra homomorphisms from LE to LF and back, which are unital and which compose to the identity maps, to maps, not to the identity maps, but to maps of homotopic to the identity. Here, homotopy refers to algebraic homotopy, that is polynomial homotopy. We will later on have occasion also for the homotopy, the notion of homotopy in the realm of C-star algebras, which is given, so you say that two star homomorphisms are of C-star algebras are homotopic if there is a continuous family of star homomorphisms that carries you from one to the other. Okay. So now I want to state the main result that I want to talk about today, which refers to lifting maps up to homotopy. So this is what I will call theorem A. It says that if E and F are SPI graphs and psi is a unital star homomorphism between C star E and C star F, then there exists a unital star homomorphism from LE to LF, such that when you pass to the completion, you get something homotopic to the star homomorphism you started with. So in other words, every unital star homomorphism between graph C-star algebras, SPI graph C-star algebras, is homotopic to an algebraic one. And moreover, the map you started with is a homotopy equivalence if and only if this map, this algebraic map phi, is a homotopy equivalence in its category, in the category of algebras. Okay? So you can lift any unital star homomorphism to a unital star homomorphism of the Leavitt path algebras up to homotopy, and if the map you started with was an equivalence, then so is this phi, and vice versa. In particular, if psi is an isomorphism, then it is a homotopy equivalence, and so it lifts to a homotopy equivalence. So you may say that the result I presented in the previous slide that we have with Diego Montero is a lift of the previous existing result of Cuntz-Krieger, in the sense that isomorphisms lift to homotopy equivalences. Notice that when I wrote phi is a homotopy equivalence in alg C, there is no star in alg C, right? Before I wrote alg upper star C, meaning the category of star algebras and star homomorphisms. So phi is a star homomorphism, but the homotopy inverse of phi, in case it has one, that is when psi is a homotopy equivalence, need not be a star homomorphism. I mean, I wish I had been able to prove that it does have a star homomorphism as homotopy inverse, but this is not, I haven't been proved that. Only that it is a star homomorphism, it has an inverse that is an algebra homomorphism. Okay. Of course, if I were a star isomorphism, then the inverse would be a star homomorphism too. Okay, so whenever there's a theorem A, there must be a theorem B, and that is the case here also. And this theorem B is used to prove theorem A. So let me talk about this in the next slide, which concerns bivariant algebraic K theory. And bivariant K theory, both algebraic and C-star algebraic. The first one I call little kk, and the second one big kk. These two are triangulated categories, which are the target of universal functors. In the case of the algebraic bivariant K theory, it is the target of a functor from the category of algebras over the complex numbers, which is the universal initial functor to a triangulated category, which satisfies a number of properties. So first of all, it is homotopy invariant in the algebraic or polynomial sense. So homotopic maps go to the same map. It is stable with respect to M infinity, that is, it sends the inclusion into the upper left-hand corner to an isomorphism, and it satisfies excision, meaning that it sends algebra extensions to triangles, to distinguish triangles. So the universal property is with respect to all these requirements or properties. In addition, it satisfies that if you set the first variable equal to the complex numbers, you recover homotopy K-theory, homotopy algebraic K-theory. This is Weibel's K-theory. It's a variant of Quillen's K-theory that is homotopy invariant with respect to polynomial homotopy. If the algebra is sufficiently regular, it's K-regular, as is the case of Leavitt path-algebras, then it agrees with Quillen's K-theory. So here I should say that the star, KKN of CA is the homomorphisms in the triangulated category KK of from C to the n-fold loops of A. So KK minus 1, say, of CA is, well, the maps from C to the suspension of A, and KK1 is the maps from C to the loops of A. Okay. Similarly, Kasparov's KK is the target of a universal initial functor to triangulate from C-star algebras. Here, C-star algebras means separable C-star algebras. To a triangulated category that is C-star homotopy invariant, meaning is homotopy invariant with respect to continuous C-star homotopy. It is stable with respect to the inclusion of an algebra, a C-star algebra, into the tensor product of the C-star algebra with compact operators, the upper left-hand corner inclusion, or the inclusion given by any rank 1 projection. And it is excisive in the sense that extensions that admit a completely positive section are mapped by the functor little k to distinguished triangles in big KK. In addition, the universal initial functor with all these properties also has the property that you recover K-theory by setting the first variable equal to the complex numbers, where here K-theory is C-star algebra K-theory, which I call K-top, is the one that is homotopy invariant with respect to this C-star algebra homotopy. So in some papers, they write K-alg for algebraic K-theory. Here I write K-top for the topological one. Okay, so there is no obvious functor going either from KK, little KK to big KK or backwards. In fact, so for example, of course, little KK contains as objects all algebras, but which not all of them are star algebras. But even if you restrict to C-star algebras, then in KK, every algebra map is represented, has a class. Every algebra map, which need not be continuous, so it does not pass to completion, it's not a star map. Whereas in big KK, you do not have anything, to map these two, any obvious gadget to map to send these two. And backwards, from big KK to small KK, you cannot go because you have properties like continuous homotopy invariance or K-stability, which do not hold in little KK. However, we will see that it is possible to define a functor from small kk to big kk, at least not all of kk, but restricted to the small full subcategory consisting of the Leavitt path-algebras of finite regular graphs. So I will write Leavitt star for the full subcategory of star algebras over C, consisting of the Leavitt path-algebras of finite graphs without sinks. And similarly, I will write Leavitt sub kk for the image of these algebras inside kk, and these are full subcategories. So I take all homomorphisms in the respective category where I put them. So the first case, I consider only star homomorphisms. In the second case, I consider all kk classes. And the idea is to extend the completion factor. So the completion factor from Leavitt star algebras to C star algebras maps a Leavitt path algebra to the corresponding graph C star algebra, and a star homomorphism to the homomorphism induced by passage to the completion. Theorem B says that this functor can be completed, can be extended to this little kk, to the full subcategory Leavitt sub kk, the full subcategory of kk whose objects are the Leavitt path algebras. Okay, so in particular, as I pointed out before, every algebra map, whether it preserves the involution or not, is represented inside this Leavitt kk, and to each of these we are associating a big kk class between the corresponding C star algebras. Right? So you can do this. So theorem says that you can do this, and well, comp, it doesn't make sense to say that it is triangulated because I mean, I didn't add the cones of all maps between Leavitt path algebras to the domain of comp, just took as objects only the Leavitt path algebras. However, the home sets in this small subcategory are this is a full subcategory of little kk, and kk between two algebras is always an abelian group, as is big kk of the C star algebras. And well, comp, this functor comp is C-linear, meaning that it defines a group homomorphism between the abelian groups of home sets in the two categories. Moreover, this functor is full, which means that it is surjective on homomorphisms. And finally, and remarkably, it is conservative, which means that comp, if you have a little kk class between Leavitt path algebras, say Xi, and comp of Xi is an isomorphism in big kk, then Xi was already an isomorphism in little kk. Okay, so let me...
Willy.
Hey, yes.
There is a question about Jean asks if homomorphism means unital homomorphism.
Where? I mean, no, homomorphism doesn't mean unital. I mean, in the original theorem A,
yes,
as I formulated it, the homomorphisms were unital.
yes.
But then they cease. They are no longer unital.
I see, okay.
When they are unital, I will emphasize it.
Okay. Thank you.
You're welcome. Okay. So I will explain how this theorem B is related to theorem A. And for this, I need to recall that in the SPI setting, when the graphs are SPI, one can relate KK, the KK groups of LE, LF, and of C star E, C star F, with homotopic classes of maps. So let me introduce some notation. I will call iota the map from the inclusion of an algebra B into the upper left-hand corner of the 2x2 matrices. And I will say that two algebra homomorphisms, phi and psi, are M2 homotopic if they become homotopic upon composing them with iota. So the way I formulated this, A and B are just algebras, and the homotopy is polynomial, but you may also talk about M2 homotopic maps between C-star algebras, and there I will mean M2 homotopic in the C-star algebra sense. Okay, so let E and F be finite SPI graphs. Then in our paper with Diego Montero, the one I cited before, we showed that that for SPI graphs E and F, KK over E and F is isomorphic to the M2 homotopy classes of maps between LE and LF with the class of the zero map removed. So this left-hand side is an abelian group, and this abelian group is isomorphic to little kk. This is, in fact, is an algebraic version of a pre-existing theorem, partly proved by Kuntz and Rordan in the Rordan paper, and more generally in Phillips' paper on Kirchberg algebras. That says that big KK of C star E, C star F is isomorphic to the M2 homotopy classes with zero removed of maps between C star E and C star F. Here I write double bracket for homotopy classes of star homomorphisms. In the literature, and in particular in Phillips' paper, these double brackets are used for asymptotic homomorphisms, but here I mean actual homomorphisms of C star algebras. Okay, so theorem B gives you a surjective map between the little kk group in the first theorem onto the big kk group on the other theorem, and tells you that, so that's the map comp, and tells you that comp of something is an isomorphism if and only if the original map was an isomorphism. So now, because the graphs are SPI, because of these two theorems, you can replace bivariant K theory by homotopy classes of maps. And so we have the completion map that assigns to a star homomorphism from LE to LF a homotopy class, an M2 homotopy class, and it maps onto the M2 homotopy classes of C star algebra maps. And moreover, comp of an element is an isomorphism if and only if the element was already an isomorphism. Okay, so this gives you part of the theorem already. If you disregard this matter of that, I mean that in the theorem A, as I formulated it, I ask homomorphisms to be unital and homotopy to be strict homotopy, not M2 homotopy. But if you allow for that, if you leave that aside for a moment, this gives you partly of what the theorem says, right? It tells you that if you have a star homomorphism from LE to LF, which happens to get mapped to a C star, because this composite is supposed to be, because of theorem B, this composite is just the completion, right? It's take completion and take the homotopy class. So it tells you that if the comp phi is an equivalence, and comp phi is the class of phi hat, then phi was already an equivalence. Okay, so let me see here. Okay, now I will state theorem A in full, a formulation that includes not only the case of unital maps, but more general homomorphisms. So it will say that you can lift up to homotopy classes of C-star algebra maps to star homomorphisms of Leavitt path-algebras, which are strongly non-zero, are strongly full in a sense, and the strong fullness condition is what I will call property P. So a star homomorphism between unital algebras and unital star algebras is said to have property P if phi 1b contains an isometry. So that is, there is an X in phi 1b such that X, so there is an X in that X star is less as a projection than phi 1, which is implied by the fact that X is in phi 1b, and so that X star X is 1. So, in other words, there is a projection smaller in the projection order than phi 1 that is equivalent to the identity. So, for example, if phi is unital, then it does have that property. So this is what in the language used in Blackadar's book, for example, this means that phi of 1 is a very full projection. Okay, so I write a superscript P for the star homomorphisms that have property P. And the first item of my theorem A is that the map from star homomorphisms to property P to C star homomorphism, M2 homotopy classes of C star homomorphisms, non-zero ones, is onto. So you can lift any non-zero star homomorphism to a homomorphism. Here I am still assuming that E and F are SPI. And moreover, the subset of unital star homomorphism maps onto the subsets of homotopy classes of unital C-star algebra homomorphisms. Okay. And if you have a homomorphism, a star homomorphism with property P from LE to LF, such that phi hat is an M2 continuous homotopy equivalence, then phi was already an M2 homotopy equivalence. And if furthermore phi happens to be unital, then phi hat is a continuous homotopy equivalence without the M2, if and only if phi is a polynomial homotopy equivalence. Okay, so this includes theorem A as I formulated it originally, and also includes the case of non-unital maps, which make M2 homotopy appear. Okay, so I told you how theorem B is related to theorem A, and how it leads to a more general, to the introduction of M2 homotopy. And I now would like to give you an idea of the proofs of these theorems. So let's start by theorem B. So the first problem is to define comp. Now, in order to make the diagram commute, so remember comp was a factor between little kk restricted to Leavitt path-algebras to big kk that was supposed to extend the completion factor. So in particular, it must send a Leavitt path-algebra LE to the C-star algebra C-star of E. So on objects it's clear how to define it. The problem is how to define it on homomorphisms. So to a little kk class, you have to associate a big kk class. And the idea for this is to use Poincaré duality. So Poincaré duality, which holds both for graph sister algebras and for Leavitt path algebras, tells you that in the bivariant K-theory category, tensoring by the corresponding graph algebra, be it the Leavitt algebra or the sister algebra, tensoring with this algebra is left adjoint to the loops of tensoring with the algebra corresponding to the dual graph. So in the sister algebra setting, this was proved long ago by Kaminker and Putnam. I observed that the same thing goes through without much modification in the Leavitt path algebra setting. And this requires, to work, this requires that the graph E be essential. So it must not only not have sinks, but also not have sources. So both the ES map and the R map must be surjective. But this is not a problem because removing sources does not change the Morita equivalence class, and therefore, and Morita equivalence equivalent algebras are isomorphic in the bivariant K-theory. So this is not a problem. And once you remove sources, you can proceed as follows. So here on the left, in the first line, we have little kk over E LF. At the end of the third line, we have big kk of sister E, sister F. We want to go from the upper left-hand corner to the right-hand corner. So here's what we do. We use Poincaré duality to pass the LE, which we regard as complex numbers, tensor with LE, to the right-hand side, where E has been changed to the transpose graph or the dual graph, which I call ET. Okay, now this KK1 is, since C is on the left, is a K-theory group. In fact, it should be a homotopic K-theory group, but by regularity result, the tensor product of two Leavitt path algebras of finite graphs is K-regular, and so KH1 and K1 are one and the same. Okay, so here you have K1 over F tensor LET. This is an algebra and has a completion, and you can go from K1 algebraic of this algebra to K1 algebraic of the completion, and which is this sister algebra, this completed tensor product. That's what the twiddle means. And you can go from K1 over sister algebra, K1 over sister algebra, to topological K1. The latter is a quotient of the former. And now we landed in K1 top of this sister algebra, and then apply Poincaré duality again to reach your destination in big KK. So one has to show that that this map, first of all, extends the completion map, and second of all, that that it maps composition to composition. If it extends completion, then it will map identity to the identity. And in both cases, the reason why this works is that the isomorphisms between the bivariant K and the single variant K are the same. The same formulas work in the algebraic case and in the sister algebraic case. So this is exactly, I mean, how you prove that phi goes to phi hat. so that it extends completion. And to prove that composition goes to composition, you take two K1 classes, algebraic K1 classes, map them via Poincaré duality to little kk, compose them, map the composition back to K1 using Poincaré duality, and do the same with their images on K1 top. And the result comes out to be the same, simply, again, because the formulas for Poincaré duality are the same. So here, I will also want to point out that this explains also how the problem of where to send a homomorphism, which is not a star homomorphism, where to send it in big KK. So, I mean, when you go from algebraic K1 to topological K1, you also have the problem that algebraic K1 is a quotient of GL, whereas topological K1, well, which can also be defined as a quotient of GL, one usually regards it as a quotient of the unitary matrices. So one knows how to pass from GL to unitary. You take an invertible G, and you consider the square root of G star times G, divide G by that, and that gives you a unitary. And that's how you convert an invertible matrix to a unitary one. And here we are using that and Poincaré duality to send the maps which do not necessarily preserve the involution to maps which do. Okay, and yeah, so this is how comp is defined. Now, why is it full? Well, we write, LE, the Leavitt path algebra of E, has a canonical presentation as a quotient of the so-called cone algebra, modulo a sum of ultramatricial algebras, which I call KE. This CE, notice it has no star. It's not the sister algebra of E, it's the cone algebra of E. LE is defined by modding out a free algebra by two main classes of relations. You simply omit one of the classes, and that's CE. Okay, and so any algebra extension gives a triangle in little kk, and in this particular case, when you pass to the completion, you also get an extension that has a completely positive splitting, and so defines a triangle in big kk. And these triangles are, as indicated in the slide, in both cases, the cone algebra and the ultramatricial algebra, the sum of ultramatricial algebras, are isomorphic to as many copies of the complex numbers as there are vertices in E. And the map connecting them is exactly 1 minus A TE. Okay, so in order to compute little kk of LE, LF, you simply take this triangle and home it on the right with LF. And use the fact that triangles, when you home a triangle in a triangulated category, you get a long exact sequence. And if you do this, so I will write the diagram that shows up. I need some notation. I will call the group that I will call the dual Bowen-Franz group is the cokernel of the identity minus AE without the transpose, which you may regard as, in the case when E is essential, this is precisely the Bowen-Franz group of the transpose graph. And this is equal to kk minus 1 of LE C. So it's the maps from LE to the suspension of C in the kk category. Okay, so we have this diagram. The left-hand corner, the left-hand column is an exact sequence. The exact sequence coming from the triangle in the previous slide. And on the right column, the injection and the slanted arrow are constitute the exact sequence coming from the second triangle, the triangle in big KK. This kernel of identity minus AFT is K1 top of C star F. Okay. And well, the map from K1 LF to this kernel is surjective. It is actually the index map corresponding to the excision sequence in single variant K theory associated to the conalgebra extension. Yeah, and well, so by a snake lemma argument, since the top guy is the top row is surjective and the bottom row is the identity, the map in the middle is onto. This proves that comp is full. Moreover, a snake lemma argument also tells you that the kernel of comp is the kernel of the horizontal map on top. And to prove, this will be important to prove conservativity, to analyze this kernel. And this is what we do in the next slide. So say pi is the canonical projection map from the cone algebra to the Leavitt path algebra. Then the image under pi of K1 of the cone algebra inside K1 of the Leavitt path algebra is isomorphic to the Bauer-Franz group of F tensor with K1 of C, which is C star. Okay, so we have this subgroup, and so this subgroup lives in K1 LF. K1 LF is KK1 of C to LF. These are the maps from the suspension of C to LF. On the other hand, we have the maps from LE to the suspension of C. Composing them, you compose a map from LE to the suspension of C with a map from the suspension of C to LF, and then you get a map from LE to LF in KK, which lies in the subgroup, which is the kernel of this partial map. And this composition map turns out to be an isomorphism. Okay, so say I want to prove that comp is conservative. So I take a KK class from LE to LF, which goes in big KK to an equivalence. So this equivalence has an inverse, which, because comp is full, lifts to a little KK class from LF to LE. So I compose, and I get a class from LE to LE, and composing in the opposite direction, one from LF to LF. So in order to show that comp is conservative, I will need to show that these two compositions are invertible, knowing that they go down in big KK to the identity. But now I have a map between endomorphism, a map induced by a functor, between the endomorphism rings of two objects, of an object and its image. So this is a ring homomorphism. And I want to show that a certain element in the domain, that if an element in the domain ring, goes to an invertible element in the target ring, then the element I started with was already invertible. And one way of showing this is showing that the kernel is nilpotent. And in fact, it is a square zero ideal. Why is this? So say I fix F, and I have two elements in this kernel, and I want to multiply them and see that it is zero. So it suffices to check that this, for the image of two elementary tensors in this isomorphism that I wrote above. So I take two elements, C1 and C2 in K1 of CF, which because CF is KK isomorphic to as many copies of C as F has vertices, this is K1 of C to the F0. And I have the elements eta1 and eta2 in K minus 1 of LFC. So when I do the product, in the middle of the product, I have eta1 composed with pi. Now pi goes from CF to LF. In KK, CF means a number of copies of C, right? So I go from a number of copies of C to the domain of eta1, which is the suspension. So how is this? Yeah, which is LF, and land in the suspension of C. So I have a bunch of maps in little kk from C to the suspension of C. So these are elements of K minus 1 of C, but K minus 1 of C is 0. So the product is 0. And that proves the conservativity. Yeah. Now I have the proof of theorem A. How am I with time, Gisela?
We've got maybe 10 minutes.
Okay. I think I can do it in 5. Okay, so that finishes the proof of theorem B. Let me go over part of the proof of theorem A, namely that the map from star homomorphisms with property P between LE and LF, E and F being SPI, to the homotopy classes, the M2 homotopy classes of non-zero homomorphisms between LE and LF, that map is surjective. Okay, so here is the diagram. On top, we have the star homomorphisms from LE to LF, which have property P. Then I want to show that the composite of the vertical maps is onto. I know it is onto starting from homotopy classes of maps between LE and LF, of algebra maps, but I want to know that it is onto starting from above. Okay. So the map 1, which is obtained by composing, I mean, all the diagrams commute there. The map 1 is onto, I put this in this paper on classification of Leavitt path-algebras up to involution preserving homotopies. So what I showed was that a homomorphism between Bauer-Franz groups lifts to a star homomorphism with property P. And moreover, that if the homomorphism between Bauer-Franz group was unital, in the sense that it sent the distinguished element to the distinguished element, then you can lift it to a unital star homomorphism. Okay, so this map label 1 is unital, is surjective. So say you have a class psi in of an M2 homotopy class of a map from C star E to C star F, and you want to lift this to star homomorphism. Then you push it down to the right via the map 2, and using the fact that 1 is surjective, you can lift this to a star homomorphism phi with property P between LE and LF, and then take the difference. So the composite of the vertical maps is the map K that goes from algebras to from C star algebras to KK, composed with completion, and this difference will be in the kernel of this map labeled 2. So what is this kernel? Okay, so we already have chosen a phi. Okay, so we take LF phi to be that sum, you can also define similarly C star F sub phi hat. And this LF phi is a direct sum of algebras, each of which is Morita equivalent to LF. So its K1 is the sum of copies of K1 of LF, as many as there are summands, and these are the number of edges. And this applies onto the kernel of the map 3. The map 3 is this one, right, at the algebraic level. And similarly, K1 top of C star F phi hat, which is K1 top of C star F to the E1, and K1 top of C star F is this kernel, applies onto the kernel of the map 2. Now, now the map, this map on the left is surjective, but because the map from K1 LF to this kernel of 1 minus AFT is surjective. But moreover, let us consider the unitary elements of LF. Rordan, in his paper, constructed an explicit inverse of the isomorphism between K1 top of C star F and this kernel of 1 minus AFT. And in our paper with Diego Montero, we observed that this also gives, the same formulas, give a section, a set theoretic section of the map from K1 LF to this kernel of 1 minus ATF. But moreover, this section associates to any element of the kernel not just the class of an invertible element, an invertible matrix in LF, but of a unitary matrix. And in the case, and here this is for any finite graph F, but here we are assuming that F is SPI. So we can roll over a matrix, an invertible unitary matrix, to a unitary element of LF. So this composite between going from the unitary group of LF to K1 to this kernel, the unitary group abelianized to K1 to the kernel, is onto. Thus, you can lift this element that we have, this difference between psi and k of phi hat, it's the image of a unitary element. And when you add an element to the image of the unitary element, what you do, and this is in Rordan's paper and also in my paper, is that you perturb phi by sending an edge E to U times the edge E. And this is a star homomorphism. So you send E star to E star times U star being the inverse of U because U is unitary. And that's your star homomorphism. So we have lifted psi first to a phi, and this was not quite a lift because they differ from an element in this kernel, and then we lifted the element of the kernel too, added up, and came up with a star homomorphism whose completion is homotopic to the xi we started with. Okay, so this finishes the proof of theorem A. Here are the references I used. The first one is where the question for Leavitt path-algebra, the Kirchhoff-Phillips problem, was first formulated. The second one is the only one that has not yet been published. It's my paper on classifying Leavitt path-algebras to involution preserving homotopy. this has been on the archive since January of this year. Then the paper with Diego Montero that appeared in 2020, the paper where Kaminski and Putnam do Poincaré duality, in the sister algebra setting, the algebraic Poincaré duality is done in the paper labeled 2. The paper by Chris Phillips on the Kirchberg-Phillips theorem, and Rordan's paper that I cited for the Kuntz-Rordan results. And that is all. Thank you very much. Gisela?
Okay, here I am. Thank you, Willy. Maybe we have some questions. Let me see.
Yes, I have a question.
Yes.
Isn't true that you have proved Poincaré duality in algebraic KK? Or
Yes, but this is already in this paper. So what I talked about today is a new result and a couple of new results which are in a preprint, which I haven't yet posted in the archive. The Poincaré duality theorem is in the paper I already posted in the archive in January.
Okay.
And it's for Leavitt path-algebras.
For Leavitt path-algebras, I mean, in the sister algebra setting, I think the newest paper that I know on Poincaré duality is this one that in which Adam Rennie is one of the authors, in Advances in Math, appeared a couple of years ago. And there, Kuntz-Krieger, he talks about Poincaré duality for Kuntz-Pimsner algebras, which are more general than the algebras. So what I did was inspired by this Kaminker-Putnam theorem, which is, I don't remember, well, I think it is in the, we can see the year of the publication, 1997, so it's more than 20 years old.
And I have a question. And ET, who is ET in the Poincaré duality?
Extraterrestrial. So it's the transpose graph. So you have a graph has an incidence matrix.
It's almost the same. Okay.
You transpose this incidence matrix, and it is the incidence matrix of another graph. That's the transpose graph.
And you have finite hypothesis. Okay.
Finiteness hypothesis. Yeah, well, you need finiteness hypothesis in anything you do in little kk because of the famous problem that we do not have
coproducts.
Yeah, infinite coproducts. But yeah.
Okay.
Okay. Any other question?
I have a question, Willie. So does this work lead you to make a conjecture one way or the other as to whether or not LV2 and LV2 minus are either ring isomorphic or algebra isomorphic or star algebra isomorphic?
Well, I mean, in the sister algebra, I mean, in the L2 minus case, I mean, this tells you that any isomorphism between C star, between ON and ON minus is homotopic to the completion of a star homomorphism between Ln and Ln minus. Now, when n is 2, there is only one class of homomorphism. So it doesn't tell you much. I mean, the only class of homomorphism that you have from L2 to L2 minus goes to the only class of homomorphism. So that's not. I would suspect that there is no isomorphism between L2 and L2 minus. So, yeah, but I mean, we all agree from the results that are in the literature that if such a homomorphism would exist, then it would be quite unusual, right? And not preserve any additional structure. So, I mean,
So this, so the current work shouldn't inform that question?
well, I mean, this current work does not tell you much about the case of L2 and L2 minus, no.
Okay.
Regrettably, but yeah.
Thank you. And when do you think you might post this new work in the archive?
Well, I mean, so I finished writing it a couple of weeks ago, then I let it sit. And now, I want to read it all again to check, I mean, the writing and so on. And then I'll post it when I'm, but the proofs are fully written up and everything.
Thank you.
Okay, well, maybe we can stop the recording now.
Yeah.